Hello and welcome to another homework helper video. For section 4.7, there aren't a lot of problems in the section because these are a little bit more involved, but there will be, don't let that fool you, there will be these problems on the exam. They will be well represented, so you want to make sure that you have these down. I've picked two that students sometimes have difficulty with, so let's jump right in. So what we have here is a ranch. We have a rancher, and this rancher, she wants to create two rectangular corrals, and it says see figure. I'm going to draw the figure for you right here best I can. So these are supposed to be two rectangles right next to each other, and the rectangles are actually the same size. I believe in the figure that they give you what they suggest for the variables. So what they do is they call x one dimension of the smaller corral, right? This is the half of a corral, right? And then they call that x on this one too because they're the same size. So what we have here is x on both sides and y for all of these lengths. And what we want to maximize here, the dimensions, what dimensions should be used so that the area enclosed will be a maximum, right? So if the area is going to be a maximum, that's what we want to optimize. We want the maximum area. Okay, so I need a formula for the area of these two corrals, and the area of all of them together is just 2xy, right? We've got x times y for one of them, and there are two corrals, so it's just 2x times y. That's what we want to maximize. So what we want to do is take the derivative of this, find the critical numbers, right, by setting the derivative equal to 0 or finding where the derivative is undefined, and then do our whole process of either first derivative test or second derivative test, however we want to go from there. All right. So it's the same thing that we've been doing for most of this chapter, since section 4.3 anyway, of finding the critical numbers and finding the relative extrema. The other thing that we want to make sure we do is we incorporate the 160 feet, right? This is our restriction. Some people call it the secondary equation. And what this restriction means is that we can't just choose any values for x and y. It has to be that we have 160 feet of fencing, right? So if you think about the total amount of fencing used to make this corral, what you have is 4 lengths of x and 3 lengths of y, right? So 4x plus 3y has to be 160, okay? So what we're going to do is use this secondary equation, solve for one of the variables, put that expression, substitute that expression into the other equation, and then use that to maximize. Take the derivative, set the derivative equal to 0, find where that derivative is undefined, and where it's equal to 0, and use those critical numbers to do our first derivative test, or maybe our second derivative test. We'll see when we get there. So I'm going to solve for one of the variables here. So subtract 4x on both sides. This is the nice, easy, comfortable algebra part. 160, oh, excuse me, I moved the whole screen. 160 minus 4x. So y is equal to 160 minus 4x all divided by 3. And I'm going to substitute that back in for y over here. So I solve for y, and I'm substituting that expression back into the function I'm trying to maximize. So a then would be equal to 2x times 160 minus 4x all over 3. Now, one of my pieces of advice for you is to always use your algebra skills to simplify the function you're trying to maximize before you take the derivative. It's much easier to take the derivative if you can simplify this to its lowest terms. So in other words, I could do the derivative right now, right? But I'd have to use the power rule, and it looks kind of complicated. But if you simplify this a little bit, it makes the derivative really easy. So I'm going to distribute the 2x, and I would get 320x minus 8x squared, all divided by 3, right? And if you think about that a little bit further, since it's just divided by 3 here, now you can say, oh, this is 320 divided by 3x minus 8 divided by 3x squared. And if you think about this as just a polynomial, then all we have to do to take the derivative is do the power rule. So it's much easier. So remember to simplify those things when you can. So what I'm going to have here is a prime. I'm going to do my derivative now, right? This is just x to the first, so that just becomes 320 over 3 minus, and this is 2 times 8 over 3, so that's 16 over 3 x. And our job is to find the critical number so we can maximize this area, right? So what we're going to have here is, first, don't forget to find where this derivative is undefined. It turns out that in this case, we just got x to the first here, right? So there's nowhere where this is undefined, but don't forget to do that. I'm going to set this equal to 0 to find my critical number. So you can multiply everything by 3. So basically what we have is negative 16 over x is equal to negative 320. I did a couple steps there. I hope that's okay. Multiplied everything by 3 to get the 3's out of there, and then just brought the 320 to the other side of the equation. Divide both sides by 16, and x is equal to 20. Right? So let's kind of want to see if 20 makes sense. That could make sense, right? 160 here, we'd have 20 here and 20 here, so this total length would be 40, and we'd have 20 here and 20 here, and that would be 40, and that would leave us plenty of room for our 3 lengths of y, right? If this length is 40 and this length is 40, that's 80. That's half of what we got. So we've got half left over to do these y sections of the corral. So 80 kind of fits inside our relevant domain. Okay, what we want to make sure of, though, is that that 20 actually represents a maximum and not a minimum, right? All we've shown so far is that it's a critical number. So let's see what happens here. We could do first derivative test or second derivative test. My general rule of thumb is if the second derivative test, if finding the second derivative is easy, if you can find the second derivative easily, then go ahead and use the second derivative test. It'll be easier. And if not, if the second derivative is going to be complicated, then use that first derivative test. But in this case, we've just got a nice polynomial function for the first derivative, so the second derivative will be relatively simple. The second derivative, okay, so this is just a constant term, right? So that when I take the derivative, that's 0. And here, it's just an x to the first, so the second derivative just comes out to be negative 16 over 3. In other words, this function is always concave down. And if it's concave down, then when I plug x in, it's going to be concave down, right? Because there's no x in here, so it's still going to be negative. And so it's concave down here, and the second derivative test tells us that at critical numbers where the function is concave down, right? Concave down means that you have a maximum. Real quick sketch. Something like that, right? And you have a maximum instead of a minimum. So with that, what we have there is a maximum value. So that shows that it's a maximum. You could use the first derivative test, but that's just going to be more complicated. I also want to make sure that I actually answered the question. It says what dimension should be used. Okay, so x should be 20, right? And then y, we have to figure out what y should be. And remember that this whole thing has to equal 160. That was our restriction. So we know that 4x plus 3y was supposed to be 160, and we just solved for x. So if x is 20, then 4 times 20 is 80. Oh, excuse me, this should have been 160, right? And if that's true, then 3y must also be 80. So y should be 80 divided by 3. I hope that makes sense to everybody. So we've got our dimensions. And I kind of think that this question is a little bit vague. It says what dimension should be used, right? Well, the dimensions of what? Do I want the dimensions of the smaller corrals, or do I want the dimension of the whole thing? I guess it means the smaller corrals. I guess each corral would be 20 by 80 over 3. That's a good way to answer the question. Or you could say the total thing would be 40 by 80 over 3. Just make sure you answer the question that they ask you, okay? That's always the key. Okay, so that's the first one. I've got another one here that's a little bit more difficult for students sometimes, so let's go through that one. What we have here is we're going to have this offshore oil well, and it's 4 kilometers to the coast. So the oil well is supposed to be up here, so maybe I should make a note of that. That up here is our oil, right? That's our oil well, right? And the refinery is located 5 kilometers down the coast. Okay, so here's the shore, right? This is the shore down here. And the oil well is 4 kilometers offshore. And down the coast, 5 kilometers, is the refinery, right? So the refinery is over here. Okay? And the question is, laying pipe underneath the water is more expensive, twice as expensive, in fact, as doing it on land. So the question is, what path should we take, right? The idea here is, if we go straight to the refinery like this, it may be too expensive because it's more expensive underwater. If you do the whole thing under the water, then it's going to be a little bit more expensive, maybe. if we go straight to the shore, and on land, that's sort of the longest option, right? We're going to be using the most pipe, whether it's underwater or on land. There's going to be a lot more pipe used than if we do underwater at an angle and then use some of the on land to make it cheaper, right? So the idea is that there's going to be some optimal path to make the cost of laying this pipe a little bit cheaper, right? So what we're interested in here, let me change colors a little bit to make it a little bit more clear. The path that we're interested in is this path. We're going to take this path to get there. And the question is, where should this location be? What should we be shooting for? Where should that be? And so I've labeled this distance, as you can see in my picture, I've labeled this distance X, because that will tell us where that location is, right? And keep in mind, the entire length all the way to the refinery is our 5 kilometers. So that's why I've labeled this 5 minus X. Whatever I used up to here, this will be the rest of it, right? This will be the 5 kilometers minus however far this is. So that's 5 minus X. And we're interested in how much this path is going to cost so that we can minimize that cost. Okay, so the first thing we're going to do is do the cost of doing the underwater section, right? So I'm calling this right here the underwater part, this diagonal sort of, right? So the cost of that section is going to be, so I'll call it the cost underwater. And what we have to figure out is how long that section's going to be, and it's sort of, we're going to use the Pythagorean theorem, right? The cost of that is going to be x squared plus 4 squared and the square root of that, right? Really what I'm doing is the distance formula, or you can think of it as the Pythagorean theorem, right? So that distance is the square root of 4 squared and x squared, right? That's its distance. And the cost here, I'm going to say that cost, we don't know how much it actually is. It just says it's twice as expensive. So what I'm doing this cost, I'm going to multiply it by a factor of 2, just to denote that it's twice as expensive as the on land part. So now for the cost on land, for laying our pipe here, that one's a lot easier. It's just going to be this 5 minus X. No problem. That's how long that is. If this is X, that part's going to be 5 minus X. Oops, excuse me, I meant 5 minus X. And I'm just going to put times 1 here. We really don't need it, of course, because it's just multiplying by 1. But just to emphasize the point that this is going to be twice as expensive as that. Keep in mind that that number is not going to matter. If I said that this was worth, I don't know how much it costs, $100 for every foot, then this would be $200. So it's relative, but that won't matter with our derivatives, right? Those are just constants. Okay, so our total cost, the function I'm going to try to minimize here, because I'd like to minimize cost and not maximize cost, right, is going to be those two expressions added together. So the cost in terms of X is going to be, I'm going to put 5 minus X. I would write times 1, but that just seems kind of silly. 5 minus X plus the other part. I'm going to write it as 16 plus X squared, all raised to the 1/2 power, times 2. I'll put the 2 in front here. Okay? So that's an expression for how much this is going to cost, depending on where we locate this X position here, right? So that's the function that we want to minimize. So I'm going to go ahead and take the derivative, c prime of X. It's going to leave me with, okay, so the 5 is just a constant. Negative X, its derivative is -1, plus, this is just a constant multiplier, so that's along for the ride, 2 times, okay, now let's do the derivative of this part. I'm going to do power rule, 1/2. Leave the inside here the same, 16 plus X squared. Lower the exponent by 1, -1/2. And multiply by the derivative of the inside. Don't forget the chain rule, right? The derivative of the inside part here is just going to be 2x. Good. Now what we're going to do is, we're going to set this, we'll do what we always do, right? We're going to evaluate this expression, set it equal to 0, find the critical numbers, and decide where this function is undefined. Also, don't forget that part. So what I get here is -1. The 1/2 and the 2 will cancel out here. So we're just left with 2x in the numerator. This is all going to be a square root in the denominator, right? So plus 2x in the numerator and my square root down here in the denominator, 16 plus x squared. Okay. So this is our derivative. Where is this function undefined? Well, keep in mind, anytime you have a denominator, you think about what x values will make that denominator 0, but that will never happen here. There's no way to make this denominator 0 because we've got x squared is going to be positive for sure, no matter what real number we put in, and we're adding 16 to it. So there's no way to make that equal to 0. We might worry about where, and we also want to worry about taking square roots of negative numbers, but again, 16 plus x squared has to be positive. So no worries there. We don't have to worry about where this is going to be equal to undefined, where this derivative is going to be undefined. So I'm going to set this equal to 0 to find our critical numbers, right? So when I set that equal to 0, what I'm going to do is I'm going to multiply by the square root, multiply every term in the equation by the radical here, right? So multiply by square root of 16 plus x squared. That makes this negative 1 negative square root of 16 plus x squared. It'll make with this term, the radicals will cancel out, right? Square roots will cancel out, so you just get plus 2x. And of course, 0 times anything is just 0 for over here, right? Okay, much better. Now we're going to bring the square root to the other side of the equation. So 2x is going to equal the square root, right? That's just adding it on both sides. And now we're going to square both sides to get rid of the radical. So squaring 2x, you get 4x squared. And squaring the radical, you just get 16 plus x squared. Okay, solving this, subtract x squared on both sides, so 3x squared equals 16. Algebra, nice and easy and friendly. X squared equals 16 over 3. So x is equal to the square root of 16 over 3, or just 4 over square root of 3. In an algebra class, I'd make you rationalize that, but I'm not too worried about that for our purposes, okay? So there you go. We've got our only critical number, and I did something wrong that I shouldn't have done. When you take the square root of both sides, you should definitely remember your plus or minus, right? When you take the square root of both sides, it could be that it's positive 4 over square root of 3 or negative 4 over square root of 3. But keep in mind, in this case, it doesn't make sense for x to be negative because x is representing a distance. So we would throw that negative value out anyway, right? So I'd have a plus or minus here, right? But it doesn't make sense in the context of our problem. Negative 4 over square root of 3 isn't in our relevant domain. It just doesn't apply to the problem. So we're just going to leave the positive answer, right? All right, so we've got that. Like I said earlier, I like to use the second derivative test when I think the second derivative is going to be simple. Here is our expression for the first derivative. I don't want to take the derivative of that, so I'm going to use the first derivative instead. Okay, so I just have to be able to find a number that is bigger and smaller than the square root of 3, than 4 divided by square root of 3. I can tell that 1 is smaller than this because square root of 3 is smaller than 4, right? So 1 is smaller. I'm going to use 1 for one of the points that I pick. Oh, I don't like that at all. It's not very horizontal. Let's try to be horizontal here. Best I can. Okay, and we're doing the first derivative test. I like to make a note of that we're doing first derivative. Okay, so I'm going to put randomly 4 root 3 in my number line, and I'm going to choose 1 for a number that's smaller. And I'm sure that 3 is larger, so those are the two numbers I'm going to pick. So what would c prime of 1 be equal to? Well, relatively simple here. Negative 1, that's a constant. If x is 1, then I've got 2 over the square root of 17. Now keep in mind, I don't care what this is actually equal to. I don't care what the number is. All I'm checking in the first derivative test is whether this is positive or negative so that I can see on this region whether the function is increasing or decreasing. I can tell 2 over the square root of 17 is a pretty small number. Smaller than 1 anyway, so I know that this is negative. I'm not going to worry about what it's actually equal to, getting a common denominator, adding those together. I don't care. All I care about is whether it's positive or negative, and I know that that's negative. Okay, so I know the function is decreasing on that interval, and then I'm going to plug in 3. The other thing you want to be careful of is when you pick these numbers, 1 and 3, you want to make sure you stay relevant to the problem, stay inside the relevant domain, right? So since the shoreline here that we're interested in is 5 kilometers long, then it makes sense for x to be either 1 or 3. Those are inside the relevant domain. Maybe x is 1, it's down here, maybe 3, x is closer to 3, so it's up here. But the idea is we wouldn't want to pick 6 because 6 would be outside of our relevant domain. We wouldn't want to pick any negative numbers because those would be outside our relevant domain, right? So we've picked 1 and 3, those are all inside. And it's also important that the critical number is inside that range. 4 over square root of 3 is inside our relevant domain as well. Anyway, trying to pick 3 here. So when I pick 3, I get negative 1 plus 6 over, held it too long, 6 over the square root of, when I plug 3 in, this is 9, 6 over the square root of 25, which is equal to negative 1 plus 6 over 5. 6 over 5 is bigger than 1, right? So this is positive. So the function is definitely increasing on that interval. So you always want to check to make sure you have a minimum or a maximum. That's part that people always forget to do. They get down to this critical number and they say, oh, there's my answer. But we haven't proved that that's going to minimize the function or it's going to maximize the function. I have just shown with the first derivative text that this is definitely a minimum because it's decreasing before and it's increasing after. So 4 over square root of 3 is definitely a minimum, and that's what we wanted to do. We wanted to find, let's see, what path should the pipe follow, right? So in other words, we were trying to find this spot. Well, what this says is we want to go 4 divided by square root of 3 kilometers down the shoreline, and that's the goal we're going to take to hit that shoreline. We're going to go at an angle until we hit it, straight to it, and then from the shoreline to the refinery, we're just going to go along the beach there. So our answer, that is our answer for that one. That one gives people a lot of trouble. I hope that helps with 4.7. You'll want to give yourself more time for 4.7 than a lot of the other sections because a lot of these problems are involved and setting them up is difficult for students. As always, if you have any questions, please email me. I'm here to help.